Solving simultaneous linear equations with a matrix inverse. Suppose you have a matrix equation of the form y equals ax, where A is a matrix, y and x are vectors, and you know A and y, and you want to solve for the vector x. There are many very interesting ways to try to solve this matrix equation, but here we'll only deal with the simplest situations. Suppose that A is a square matrix. That means it has as many rows as columns. If the columns are linearly independent, then there will be an inverse matrix, such that A times A inverse equals A inverse times A equals I, the identity matrix. Also, I'm assuming the matrix is well conditioned. That's the COND command if you're using MATLAB. Now take the original matrix equation y equals ax and multiply both sides from the left by A inverse. Going through the steps explicitly, we have A inverse times y equals A inverse times A times x. But A inverse times A is simply I, the identity matrix. So at the bottom we have A inverse times y equals x. Thus, if the A matrix has an inverse, the equation is solved quite simply. Let's try an example of using the solution to the equation. We'll try two simultaneous, that means coupled, linear equations. x1 plus 3x2 equals 7, and 4x1 plus 2x equals 11. So we're going to try to solve these together. Let's rewrite these two coupled equations in matrix form. The A matrix is 1, 3, 4, 2 times the x vector equals the y vector 7, 11. Again, it is easy to see that this equation is in the form ax equals y, or y equals ax. We'll just rewrite the column vector x1, x2 as x with a little arrow on top. Methods for finding the inverse of a matrix fall outside the scope of this video, so you'll have to get a scientific graphing or engineering calculator, or use MATLAB, Mathematica, LabVIEW, some program like that, to find the inverse of the matrix. Here it is, in case you don't have such a calculator. It's always nice to check your work. Here A inverse times A is in fact equal to the identity matrix, and A inverse is also equal to the identity matrix. Now remember the procedure for solving the matrix equation ax equals y. Pre-multiply both sides by A inverse, as shown for the example. Now on the left-hand side we multiply the two matrices A inverse times A and get the identity matrix. The identity matrix times the x vector is just the x vector again. And on the right-hand side, we multiply A inverse times the y vector. So, we have found the solution of the simultaneous equations given the A matrix and the y vector. x1 equals 1.9, x2 equals 1.7. It's always a good idea to check your work, so we plug x1 and x2 back into the original equations. Now we just multiply things together and add them up. And sure enough, we get our original answers, 7 and 11, for y1 and y2. Thus, the x1 and x2 we have calculated are correct. If your A matrix is well conditioned, that means it's not very close to being a singular matrix, or the determinant of the matrix is far away from 0, or the columns are independent. This should work for very large matrices, but you have to have good precision on your floating point arithmetic. So to recap, we started off with the matrix equation y equals ax, where the vector y and the matrix A are known. We multiplied both sides of the equation from the left-hand side by the inverse of the A matrix. Since A inverse times A equals the identity, we're left with A inverse times y equals x. Thus we find ourselves in the happy circumstance of having solved this linear matrix equation.